Dear students, this is Lisa Annie Joseph, Assistant Professor, Department of Applied Electronics and Instrumentation, Rajagiri School of Engineering and Technology. Today, I am going to make a presentation on MEMS accelerometers. It is a topic in AE364 MEMS for S6 students of Applied Electronics and Instrumentation of Rajagiri School of Engineering and Technology. As I start my presentation, I would like to make a note of the references that I have used to make this presentation. As I discuss about acceleration sensor, which is also known by the name accelerometer. Most accelerometers are built on mechanical vibrations. Accelerometers are used to measure dynamic forces associated with moving objects. These forces are related to velocity and acceleration of the moving objects. A typical accelerometer consists of a proof mass supported by a spring and dashpot for damping the vibrating proof mass. Let us now look into the model of an accelerometer. An accelerometer can be modeled as a second order spring damper system. When an acceleration A is applied to a proof mass M, suspended by springs with spring constant K and having a damping C, then the force F acting on the proof mass is given by Newton's law. Force is equal to mass into acceleration, or F is equal to M into A. Now, such an elementary model is actually shown in this slide. Let us now look into the other possible configurations of an accelerometer. The principle of an accelerometer can be demonstrated by a simple mass attached to a spring that in turn is attached to a casting as shown in figure A. The mass used in accelerometers is often called seismic or proof mass. In most cases, the system also includes a dashpot to provide a desirable damping effect. A dashpot with damping coefficient C is normally attached to the mass in parallel with the spring. So this can be illustrated in figure B. However, for accelerometers built in miniature, the coil spring and dashpot shown in figure A and B occupy too much space. So, alternative arrangements of components are to be made to obtain a smaller sized accelerometer. Let us now look into the further configurations of an accelerometer, taking into consideration all these aspects. The basic configuration of micro accelerometer includes a casing that contains either a cantilever beam and an attached mass as illustrated in figure C, or a hanging mass from a thin beam or diaphragm as shown in figure D. So these are the various possible configurations of an accelerometer. So put together, the accelerometers can be in general expressed as in the slide. So it contains a mass M supported by a spring K with constant K and a dashpot with damping C. All of them attached to a casing and the accelerometer is now shown to be attached to a vibrating solid body so that measurements in line with acceleration can be measured. Let us now look into the operating principle of an accelerometer. If we can represent the instantaneous displacement of the mass induced by the attached moving solid body, measured and recorded with respect to time as y of t, then the associated velocity v of t and the acceleration a of t may be obtained by the following derivatives. So, the velocity v of t can be expressed as dy of t by dt, and the acceleration a of t can be expressed as d squared y of t by dt squared. In miniaturizing the accelerometer to the micro scale, there is no room for the coil spring and the dashpot for damping on the vibrating mass. So, alternative substitutes for the coil spring, dashpot and even the proof mass need to be found. So, with all these things in mind, let us now see how a micro accelerometer will be fabricated. So here, in a micro accelerometer, the mass is actually represented by a minute silicon beam. The spring is represented by the cantilever structure that supports the mass, and the damper is nothing but the air that is in the surrounding space. So, in case of micro accelerometers, with all these arrangements, it can be realized as micro devices occupy very limited space. So, a micro accelerometer can be realized with a minute silicon beam with an attached mass, which constitutes a spring mass system, and the air in the surrounding space is used to produce the damping effect. Acceleration or deceleration is related to the driving dynamic force. So, the vibration of the body to which the casing is attached gives an accurate measure of the acceleration. Piezoelectric, piezoresistive, capacitive and resonant members are used as signal transducers in micro accelerometers. Now, having understood the basic principles of an accelerometer, let us now look into the types of micro accelerometers. The first and the prominent among them is the cantilever beam accelerometer. Let us now look into how this cantilever beam accelerometer is fabricated. In this design, the cantilever beam is actually representing the coil spring, and the surrounding viscous fluid will actually represent the dashpot for damping of the proof mass. So the representation is also shown in the slide. The movement of the proof mass carried by the attached piezo resistor. Another type of micro accelerometer is the balanced forced micro accelerometer. Now, in a balanced force micro accelerometer, let us look into what are the design adaptations. Actually, it is this concept which is actually used in the airbag deployment sensors in automobiles. So, in this design, the beam plate will act as the proof mass. The two end tethers will act as the spring. The surrounding air will act as the dashboard. So in the illustration, we can see the two end tethers, which is acting on as the spring, and the plate beam will act as the proof mass. Now in this picture, you see that there is a movement of the beam. So as the beam moves, here you have the fixed electrodes as well as the moving electrode. So as the beam moves, you can see that the fixed electrode remains fixed, but at the same time, the moving electrode comes closer to one of the fixed or the stationary electrodes. Now, the movement of the proof mass is carried out by measuring the change in capacitance between the pair of electrodes. So here, the change in capacitance is taken in for the measurement. Now the third type of a micro accelerometer is the parallel plate accelerometer, which again utilizes the capacitive effect. So here we have the illustration shown, which is that of the earliest fully integrated capacitive acceleration sensor, which is surface micro machined on a wafer with integrated MOS detection circuitry. The sensor consists of a metal coated oxide cantilever with a 0.25 microgram thick electroplated gold patch at its distal end, which serves as the proof mass. The length, width and the thickness of the cantilever are 108 micrometers, 25 micrometers and 0.46 micrometers respectively. The counter electrode is made of heavily doped P-type silicon. The capacitor gap CB is defined by an epitaxy silicon layer grown on the silicon surface. So any movement in one of the movable plates can be recorded and measured for the corresponding acceleration of the proof mass. With that, I end this presentation. In my next presentation, I will be discussing about pressure sensor. Thank you.